Hello, this is Deborah Barrett with the Cincinnati State Physics Department presenting Moving a File Cabinet, How Force Controls Motion, Part 1. Let's read through the problem first. You need to move a 920 Newton file cabinet. The kinetic friction force between this file cabinet and the floor is 368 newtons. You're in a big hurry, so you're not going to spend time emptying the drawers first. You bend down some so you can push on the cabinet horizontally. Suppose you push horizontally on the file cabinet with 505.5 newtons of force, and it doesn't move. You next push with 506.5 newtons, and it jerks into motion. Let's say the maximum static friction force is 506 newtons. What is the acceleration when the cabinet starts moving? Well, that's a lot of information in the problem statement. You may want to pause the recording and reread it. What I think I'm going to do first is draw a free body diagram for the 920 Newton file cabinet. I'm going to oversimplify a little and just use a little dot to represent the file cabinet. Next, I'll draw the forces that are acting on the file cabinet when I'm pushing with 505.5 newtons. So I'm going to draw the gravitational force, which is vertically downward. Of course, the gravitational force acts straight downward. And since the cabinet was described as a 920 Newton file cabinet, I will label that gravitational force with 920 newtons. Next, I think I'll draw the normal force on the cabinet. You remember the normal force is the support force, which always acts perpendicular to the surface providing the support. Since I didn't mention anything about the floor being crooked or being on a ramp, I will assume the floor is level, and so I will draw the support force, the normal force, as being vertically upward. So there's my normal force. The problem didn't tell me explicitly how big the normal force is, so I'm going to wait to decide that until I've got all my other forces drawn. Next, we know that I'm pushing horizontally with 505.5 newtons of force. If we assume that push is to the right, then I can draw that in. Now, if we are pushing with 505.5 newtons of force and the file cabinet doesn't move, we know there's a friction force. We also know that the friction force always opposes the motion, so we can draw that friction force opposing the motion. That will be parallel to the floor, or in this case, horizontal. So here are the forces that were indicated outright in the problem: a friction force, a normal force that we know have to act, the applied force that was actually stated, and the gravitational force. Now we can use Newton's laws of motion to determine how big the friction force is and how big the normal force is. Since the file cabinet maintains a constant velocity while the 505.5 newtons is acting on it, in this case it's a constant velocity of 0, then we know that those horizontal forces have to be balanced. So we know that the friction force is also 505.5 newtons. And since the file cabinet does not change its vertical velocity, it's also maintaining a vertical velocity of 0, then we know the normal force has to equal the gravitational force. So this is the free body diagram for the file cabinet when you're pushing with 505.5 newtons and the cabinet does not move. That's not really what the problem is about, though. The problem is about when the cabinet jerks into motion if you push with 506.5 newtons of force. we are going to assume that the maximum static friction force is 506 newtons. So we want to know what's the acceleration when the cabinet starts moving. So I need to revise my free body diagram. The cabinet still weighs the same amount, so we'll still have 920 newtons for the gravitational force. And because there are still going to be friction forces and applied forces and normal forces, I will leave those labels in place, but I'm going to erase the amounts of those forces to start a new free body diagram for when the cabinet starts moving. So when the cabinet starts moving, we've got 920 newtons of force pulling downward because of gravity, and 506.5 newtons of force pulling horizontally or pushing horizontally, because that's what you are applying. If the maximum static friction force is 506 newtons, then at the moment that the cabinet starts moving, that's how much friction force you have. Since there are no other forces acting on the cabinet besides the normal force, and the cabinet is still not accelerating vertically, we can still assume that the normal force is the same size as the gravitational force. So here's our completed free body diagram for the moment when the file cabinet starts to move. It's like a snapshot. The question asks, what's the acceleration when the cabinet starts to move? At this stage, we want to choose our relationship, and if you think about it, you have all the relationships from Chapter 2 relating to acceleration. But all of those relationships require that you have information about time, or displacement, or velocities. And although you know your initial velocity here would be 0, you don't have any other information about the time or the displacement or any other velocity. So it's not enough information to use one of the equations from kinematics. What we can do instead is use our new equation, our new discovery that there is a relationship between the motion of an object and the net force acting on the object, that the acceleration equals the net force divided by the mass of the object. So we're looking for the acceleration, so I'm going to fill in the net force that's acting on the file cabinet. The two vertical forces are going to cancel, so they are not going to contribute to the net force. But the horizontal forces are not quite going to cancel. We've got 506.5 newtons of applied force, and then we've got 506 newtons of friction force. Since those act in opposite directions, in order to give the net force, we will have to subtract those two. Then we have to divide by the mass of the object. Please don't put 920 newtons in here as the mass of the object. You know that 920 newtons is the force on the object, specifically the weight force, so you have to calculate the mass. And of course, you also know that W equals mg. I'll work that out down here on the bottom, since W equals mg, then the mass will equal the weight divided by the acceleration due to gravity, or in this case, 920 newtons divided by 9.8 meters per second squared, which works out to be 93.9 kilograms. So I am going to use 93.9 kilograms as my mass in the main formula. This numerator simplifies to half of a newton, So we have half of a newton divided by 93.9 kilograms, which works out to be 0.00533. And when you break the newton down into its component units, you've got kilogram meter per second squared being divided by 93.9 kilograms. So the kilograms are going to cancel, leaving us a unit of meter per second squared, which is what we would expect for an acceleration. Please notice that when you're working the problem, if you have fractional units, it's best to write those fractional units vertically, like I did here in the mass weight calculation, so that it's easier to see how the units cancel. This gives us our answer to the acceleration when the cabinet starts moving. Please go on to look at the second video in this series.